Hello again, welcome back to Journeys to the Ice, the podcast of the Antarctic Research Centre. I'm Matthew Wood. To determine the age of a soil is usually not a particularly challenging affair. Find some organic carbon, and providing the soil has been active during the last several tens of thousands of years, you'll be able to work out its age using the well-established radiocarbon dating method. But what about much older soils such as those in the McMurdo Dry Valleys of Antarctica? The soils of this polar desert are thought to be up to 14 million years old. Beryllium-10 is a radioactive isotope that continuously forms in the troposphere from the bombardment of oxygen and nitrogen nuclei by cosmic rays. This atmospheric radionuclide quickly adheres to aerosols and falls to the Earth's surface in precipitation or by dry fallout, and is incorporated into developing soils. With a half-life of 1.5 million years, atmospheric beryllium-10 was proposed to be the ideal radiometric clock with which to measure the absolute ages of such ancient soils. In late 2005, Martin Schiller of the Antarctic Research Centre travelled to the lower Right Valley to put this theory to the test, and ended up unearthing a story that suggests the current arid conditions of the dry valleys might not date back as far as was previously thought. Welcome, Martin. It's great to have you on the show today.
Thanks, Matt.
So today we're going to be talking about atmospheric beryllium-10 and McMurdo Dry Valley soils. Now this is work that formed the basis of your master's thesis, so we're going to be rewinding the clock 3 years or so. But in fact, just this week you've completed your PhD thesis. What sort of work did that more recent project involve?
My PhD was based on magnesium isotope studies of meteorites. So essentially a similar thing to my master's, just looking at different isotopes of magnesium, and they can be used to date relative events in the early solar system. You can look at planetesimal formation and differentiation in the first 4 or 5 million years of our solar system. So it's a very high resolution chronology of a time which is 4.5 billion years ago.
So your background's very much in geochemistry and geochronology.
Yeah, it's mostly isotopic studies, I guess. So I'm an isotope geochemist, maybe, yeah.
So the study area for your master's research was in the McMurdo Dry Valleys. To start with, could you explain what the dry valleys are and why they're unique in Antarctica?
The dry valleys are a region in the Transantarctic Mountains which are ice-free. And the reason for that is that Antarctic ice can't flow into them anymore because the mountains have risen up too high, so they built a natural barrier there. But also the climate in these regions is so dry that the sublimation rate, so the evaporation, is much higher than the actual precipitation rate. It's a desert environment, and that makes them dry, and when you go there now it looks like any desert you can imagine.
So presumably also a very ancient landscape.
Yeah, that's what the thought is.
Now I'm not too good with my chemistry, and I'm sure some people listening could do with some revision as well. Could you explain what this atmospheric isotope beryllium-10 actually is, how it's made, and how it ends up on the surface in things like soil profiles, snow and ice packs, and so forth, for us to measure?
Beryllium-10 is actually produced everywhere in the atmosphere and on the solar surface as well. We have cosmic ray radiation coming in on the Earth's surface, and it's hitting oxygen isotopes, nitrogen isotopes, and then produces a spallation reaction. So basically you split the atom and you lose a helium atom and are left over basically with a smaller core, which is then beryllium-10. And you can produce it in the rocks itself, that's in situ beryllium-10, but you can also produce it just in the air, in the atmosphere, and that's when we call it atmospheric beryllium-10. Beryllium itself is very particle active, so as soon as it's produced, it will react with something to attach it to this. And so if you produce in the atmosphere, it normally finds some dust particles, attaches to the dust particle, and then floats around with that one. So in temperate regions, most beryllium-10 in the atmosphere is actually removed by rain, so it's washed out essentially. But in Antarctica, where it's so dry, we don't actually have enough precipitation. So there it's mainly actually falling slowly out of the atmosphere. So it's like rainfall or snowfall that you can't see essentially.
So the traditional view of the McMurdo Dry Valleys in a nutshell is that it's been a relatively stable desert environment since the mid-Miocene, so 14 million years ago or so. And your study, I guess, was aimed at shedding some light on whether this view is correct or not by figuring out how old the soils actually are. The Paleosol, or the old soil that you uncovered, was overlain by this known 3.9 million year old ash deposit. So what was this ash? How did it help in building your age model? And I guess, In what way was beryllium-10 thought to be able to contribute to the dating of that soil profile?
Well, first of all, the problem why we actually went there is because we want to see if the beryllium-10, which is a short-lived radionuclide, so it actually decays over time, if we can use it to date the soil profiles. We do this in temperate regions where the soils are much younger, 15,000 years maybe, it's possible. But then we went to see if we can go into dry valleys to actually find out how old the surface really is. At this particular site where we went to, there's this so-called hard ash. So it's a volcanic ash, which is quite common in the dry valleys to find these ashes, but this one was actually dated as well. And supposedly it was lying nicely on a paleo surface. So we went there, dug 4 holes, I think in total, and only in one profile we actually found the soil undisturbed. And every other one, it was slumped and mixed with gravel, so we couldn't really use it there because we weren't sure about if it's originally land there. So the advantage in the case where you have ash fall is that you can say, well, the ash fell down and was lying there and hasn't been moved since then. So you know exactly if you date the ash by a different method, then you know exactly when the ash fell and when the underlying soil stopped to form. So that's basically the presumption. And then we looked at the beryllium-10 profile throughout this whole soil profile and try to understand what's the age mechanism we get from the beryllium-10 system. Can we actually date the soil with beryllium-10?
So far we've been talking about the radioactive isotope of beryllium, but there is of course also the stable isotope, beryllium-9, which is commonly found in soil profiles as a weathering product. Now, in a paper by Graham et al., published in 2002, those authors proposed a decay-based dating model for Antarctic soils that would supposedly provide absolute ages based on the concentrations of beryllium-10 with depth in the profile relative to the concentrations of naturally occurring beryllium-9. But you found that ultimately the method wouldn't work for your situation, and as I understand it, that was partly because the lab methods weren't really designed to accommodate such large amounts of this volcanic ash.
Yeah, I mean, volcanic minerals are quite rich in beryllium, actually. It's a lot of glass, and glass is easy to dissolve. So in order to get beryllium-10, we actually have to detach it from the particles. And you do that by leaching it in 6 molar HCl, which is reasonably strong acid at hot temperature for a while. So you actually dissolve also parts of the material it's attached to. When you have fine glass particles, you actually dissolve a lot of material, and then you actually end up with a lot of beryllium-9 in this case. So beryllium-9 has been used by Graham et al. When they presented their method to normalize their concentration with depth on the assumption that the beryllium-10 and beryllium-9 move downwards in the profile together. But when we dissolve ash particles and we dissolve soil particles, you get highly different concentrations of beryllium-9. And it just shows you it's not the 9 which is moving, but it's just the amount of dissolved material when you analyze your sample which produces beryllium-9. So normalizing to beryllium-9 is just creating an artificial depth profile of beryllium-10 essentially, which is not representing the actual truth abundance. So that basically was a nail in the coffin for trying this approach.
As you mentioned earlier, the dry valleys generally aren't accumulation areas for snow, and in terms of sediments, the gravel lag on the surface suggests that the underlying ash is actually actively eroding. Now you've calculated erosion rates for the ash and for the underlying Paleosol based on the measured inventories of beryllium-10 in those horizons. But presumably to complete these calculations, you also need to know the expected background input of atmospheric beryllium-10 into the system.
That is the big problem, this whole thing. And we use Taylor Dome, which is 150 kilometers to the southwest, I think. And that is a site where there's ice accumulation happening, snow accumulation happening, and beryllium-10 is being locked into the ice, and you can actually measure it then over time, so you get a very nice time resolution of actually the production and fallout of beryllium-10 there. But the problem obviously is that this is an accumulation site, and we're looking at a desert environment where the opposite is happening in the end. If we would have had snowfall at the site where we're digging, we probably would see the same rate. The production rate of beryllium-10 globally is very similar everywhere. It's really depending on your precipitation and your dry fallout, how much beryllium-10 you actually accumulate.
So let's look now at the nature of beryllium-10 with depth in the profile. You've shown that the in situ heart ash is basically devoid of beryllium-10. So you can be fairly certain that the profile is currently inactive in terms of downward migration of atmospherically derived beryllium-10, and has been for the last 3.9 million years at least.
The only beryllium-10 we find on the surface is really just in the sand, which is mixed around by wind. As soon as you hit pure ash, and we know by analyzing it actually that it's in situ, so we know that it has moved, it's devoid of any beryllium-10. So you can be very confident there's no migration happening. It's quite clear that the surface of today and the paleosurface, Paleosol, are independent of each other.
And so today, while there is beryllium-10 landing on the surface from the atmosphere, it's basically being whisked away by the wind before it has any effect on the profile.
That is the hypothesis, because we have to explain why our inputs that we have at Telodome are so much higher than we actually can estimate from the soils at our site. When we look at beryllium-10 concentration at the surface there, these soils would erode at a very high rate if there would be actually soil eroding and not just the beryllium-10, which is probably more likely the case.
Now, immediately below that ash in the Paleosol, there's a significant concentration of beryllium-10, and from there the concentration decreases with depth in the profile. So we're faced with the problem of explaining how the beryllium-10 got into the lower profile in the first place, prior to the deposition of that ash. Now, the dry valleys are famous for what's called patterned ground, these polygons of flat, frozen ground that look like giant mud cracks, and these can very gradually move particles throughout the soil profile. Could this process be used to explain how we see beryllium-10 at depth?
Not really. In this side, it's on a slope and it's not patterned ground. We have no evidence for any pattern there. Also, for patterns, you actually need soil moisture. So this only works actually if you have an ice-cemented ground. So there's no evidence that there could be any cryogenic transport.
And as I understand it, this kind of ice reworking or cryotubation is very effective at overturning and sort of homogenizing the profile.
Yes, that's right. Because you have a top surface input, you produce a exponential decaying profile with depth based on the retention of particles with the matrix, essentially. If you would turbate the system, you actually would homogenize the whole thing. You would end up with a non-decaying, randomly flat pattern.
Which, of course, is not what we see. Now, you point out that, alternatively, beryllium-10 can travel downward through the soil profile in solution, providing that the water is highly acidic. Considering the setting, is there any potential of generating such acidic solutions from the small amounts of snowmelt typical of current conditions?
So, we're talking about pHs which are really low, below 4 and 3. And the problem is that we are pretty close to the ocean where we are. So you get a high influx of ocean salts. And these are actually all alkaline. So the soils themselves close to the oceans are very alkaline soils. When we actually look into the ash horizon above the Paleosol, we actually had up to 70% of the weight of the actual ash was made up of salt. And this was all sodium chloride, which is sea salt essentially. So there's no real way to have produced acidic conditions to percolate beryllium-10 downwards.
And so what do you think is the most likely explanation for what we see?
We have an order of magnitude higher concentrations of beryllium-10 prior to this deposition of the ash. So in order to get it down, the only way, essentially, because we know it's alkaline conditions, it will be clay particles, it has to be attached to, and you will need some kind of liquid water, which is a rare thing in the dry valleys nowadays. That's the only way to percolate the material down into depths of 90 centimeters in a profile. So the question is now, how warm does it have to be for that, or how much water do you need? And I guess I can't really tell, but the only thing I can say is that you need liquid water, and it can be either snow melt if you have large amounts of snow, or you have occasional rainfalls. You don't need them daily. Even if it's once or twice in a century, it probably would be enough. The surface concentration of the Paleosol, when I reconstructed for 4 million years of decay of beryllium-10, is actually in the order of temperate zone profiles. So it means that there was very efficient washout of beryllium-10 out of the atmosphere into soils at that time. The problem today is that precipitation is below the evaporation rate. So it's a clear change from moist, wet conditions to extreme dryness.
So this finding really calls into question the notion that the dry valley's environment has been relatively stable since 14 million years ago. And in your paper, you refer to other recent studies that point to significant climate variability in this area during the Pliocene. What are some of these other lines of evidence?
The biggest line of evidence, I guess, is the open water conditions in the Ross Sea, which is reasonably close to the sample site. We were at a low elevation site at 400 meters above sea level. So if you have at the same time open seawater conditions in the Ross ice shelf region, like the Andrews program suggested, then that's working very nicely actually with what we find on land. The problem is that there is no on-land record. All the records we have so far are basically offshore drill sites, and that's the reason why we think it's warm, but there's no evidence. As you said, people think it's 14 million years and older, but it's because we just don't have any line of evidence. We have nothing to date the material we find, so we just assume it's that old.
So when it comes to late Cenozoic climate variability in the McMurdo Dry Valleys, it's really a matter of absence of evidence rather than evidence of absence.
Kind of, yeah.
Well, thanks a lot for joining us, Martin, during what must have been a very hectic week, and all the best for your upcoming postdoc position in Denmark.
Thank you.
For more journeys to the ice, visit sciblogs.co.nz/journeys to the ice.